Welcome, everyone, and a massive shout out to all the bright minds in our Grade 7 Advanced Girls classes joining us today. I am so thrilled to guide you through this super fun explainer. We're going to break down the invisible rules that control how literally everything around us moves. Today's guide, put together by the wonderful Musarat Jehan, is called Force, Acceleration, and You. And honestly, it's going to completely transform the way you see the physical world. Whether you're riding a bike, dropping a pencil, or just sliding across the floor in your socks, there's some seriously fascinating science behind it all. So let's just jump right in.
Okay, real quick, here's our roadmap for today so you know exactly where we're heading. We've got 5 main stops. Number 1, pushes, pulls, and motion. Number 2, Newton's second law. Number 3, the force of friction. Number 4, calculating net force. And finally, number 5, balanced versus unbalanced forces. Let's go.
All right, starting off with Section 1, pushes, pulls, and motion. We got to cover the absolute basics of motion to understand exactly what makes things change their movement in the first place.
So, here's the crucial point. Anytime an object changes its motion, a push or a pull is the reason why. No exceptions. In science, we simply call this a force. Now, when an object changes its motion, whether it speeds up, slows down, or, even just changes direction, we say its velocity is changing. And when velocity changes, the object is accelerating. It's really important to remember that acceleration isn't just about mashing the gas pedal and going faster. Hitting the brakes or turning a corner, yeah, that totally counts as acceleration too. And literally none of that happens without a force.
Just think about your morning routine for a second. From the moment you wake up, you are basically a force machine. When you're squeezing that toothpaste tube, or pressing down on piano keys, or pulling a chair back to sit down, you're applying forces everywhere. We call these contact forces because, well, they happen when one object directly touches another. It's all connected. Even lightly typing on a computer keyboard uses a tiny, weak contact force, while giant rock slabs deep in the Earth's crust use massively strong contact forces to push up entire mountain ranges. Pretty wild, right?
Okay, moving right along to Section 2, Newton's second law. This is where we explore the actual relationship between force and acceleration, courtesy of the famous Sir Isaac Newton.
So Newton's second law of motion tells us exactly how force and acceleration are linked. The formula is simply A equals F divided by m. The A stands for acceleration, F is the net force, and m is the mass of the object. But what does this actually mean in easy English? Well, if you want something to accelerate, you basically have 2 choices. You either need a lighter mass or you need a much bigger push. If you apply a larger force to an object, you're absolutely going to get a greater acceleration. They go completely hand in hand.
Which brings us perfectly to Section 3, the force of friction. Get ready to meet the ultimate disruptor of motion in our everyday world. Picture this. I want you to imagine a baseball player sprinting as fast as humanly possible and then diving headfirst toward a base. Now, according to the strict rules of motion, an object that's moving should just keep on moving, right? So why doesn't the player just keep sliding forever across the entire field?
Well, the answer is friction. The ground is actually pushing back against the player with a sneaky, invisible force. Friction is a contact force that resists the sliding motion between 2 objects that are touching. And here's the absolutely vital detail you gotta remember. Friction always acts in the opposite direction of the motion. So the player's body wants to shoot forward, but the friction from the dirt pushes backward, causing him to slow down and eventually stop entirely.
To really wrap our heads around this, let's talk about an awesome experiment designed by a student named Caleb. Caleb wanted to test exactly how different surfaces affect friction. So he took 3 identical wooden blocks and slid them down 3 completely different ramps, one made of smooth wood, one covered in carpet, and one made of rough sandpaper. Using a stopwatch, he measured exactly how long it took the block to reach the bottom. In this setup, the type of surface is the independent variable. That's the thing he purposely changed. The time it took is the dependent variable, the thing he's measuring. And brilliantly, Caleb used the exact same wooden block every single time to keep the mass constant. That way he knew for sure that any change in speed was purely because of the friction from the different textures. And no surprise, rougher surfaces like that sandpaper produce way more friction than the smooth ones.
All right, on to Section 4, calculating net force. Let's see how all this builds when multiple forces team up, because honestly, in the real world, there's rarely just one single force acting on an object at a time.
So net force is just the total sum of all the forces acting on an object at any given moment. Imagine Lizzie is pushing Alex on a scooter. Lizzie is pushing with 75 newtons of force to the left. But now, Alex decides he wants to help out, so he pushes along with 20 newtons of force also to the left. Because they're both pushing in the exact same direction, it's super easy. We find the net force by simply adding them together. 75 plus 20 gives us a total massive net force of 95 newtons to the left. See? When forces work together, they create a much bigger combined impact.
And finally, we have arrived at Section 5, Balanced versus Unbalanced Forces. Time to uncover what happens when forces actually fight against each other.
Imagine two students, let's call them Student A and Student B, pushing on a really heavy box from totally opposite sides. Even though they are both pushing incredibly hard, the box is not moving a single inch. Why? Well, because the forces are perfectly balanced. Student A's push to the right is exactly 100% equal to Student B's push to the left. They totally cancel each other out, giving us a net force of 0. And remember Newton's first law? If the net force is 0, the motion of the object does not change. Since the box started at rest, it's staying at rest. So how could they actually get it to move? They need unbalanced forces. One student could just ease up and push softer, or they could both run to the same side and team up. The very moment that net force becomes greater than 0, boom, that box is going to accelerate in the direction of the stronger push.
Now here's a really cool fact. Balanced forces don't just happen when things are sitting perfectly still. They also happen when objects are moving at a steady, constant speed. Think about a parachutist falling from an airplane. You've got gravity acting as a force pulling them straight down toward the Earth. But as they fall, air resistance is pushing right back up against that parachute. Eventually, that upward push of air resistance perfectly matches the downward pull of gravity. The forces become balanced, and the net force hits 0. Now, this definitely does not mean the parachutist magically stops moving in midair. That would be terrifying. What it actually means is that their motion stops changing. They stop accelerating, and instead, they just fall at a steady, constant speed, which scientists call terminal velocity.
To wrap up our amazing session today, I want to leave you with a completely wild thought to ponder. Newton's first law says objects in motion stay in motion unless a force stops them, and objects at rest stay at rest unless a force moves them. We just learned that friction is the force that slows us down, but it's also the force that allows our shoes to grip the ground so we can push off in the first place. So, imagine if someone just snapped their fingers and magically turned off all the friction on Earth. What would actually happen if you tried to run down the hall to your next class? Just think about how your shoes would even interact with the floor. Thank you all so much for joining me today to explore the invisible forces shaping our world. You grade 7 girls are amazing. Keep observing, keep questioning, and definitely keep accelerating your knowledge.